All right, folks, we are back. We are studying chapter 4.2.2 on maximum likelihood solution for our data when we're trying to do classification. So what's the big picture here? So in the previous case, what we were given was we had, let's say, two clusters, and we were given that they both had the same covariance. So there's one of them right there, and it's got some mean. And there's another cluster right there, and it's got its own mean. And we found, and our job was to find the line that would kind of separate them, basically, right? So we're given the parameters of the two clusters, and we want to find the separating the decision boundary. And it turned out that it was linear because we assumed the same covariances. So the setting in this particular section is just slightly different. We're not given these values. We have to estimate them from the data. So instead of being given these covariances, you're going to be given, let's say, a bunch of data points. So there's some data points here, and there are some data points here. And now you have to estimate, okay, these means and the common covariance. And then once you've got that, then you can go and do, figure out the decision boundary, whatever it is you want to do. Okay, so that's what we're going to do. We're going to get into it. It's very simple. There isn't very much going on. So the only, all you have to do is you set up your data likelihood and you maximize it. And, like Richard Feynman always said, it's always good with problems to try to guess what the answer is beforehand. And the answers that come out of this, as is often the case with maximum likelihood in these settings at least, is very intuitive. So what you end up finding is that, your class priors just count the fraction of your data points that belong to one class versus the other. Your means just add up taking the averages of the two clusters. So they're labeled, right? So you can just get those averages. And the covariance ends up becoming the average of the covariance of the two clusters. So you need to come up with a common covariance. What covariance would you guess that it would be? Well, it would be a weighted average of the covariances of the two clusters. So that's exactly what comes out of this analysis. It's very straightforward. So the only bits of it I'll really comment on, and it doesn't require much comment, is taking the derivatives with respect to covariance, because the rest is really just a matter of setting up the problem and computing some very basic derivatives. Okay, so let's just do that. Very simple. Let's go through the text. Okay, so he says, once we have specified a parametric functional form for the class conditional densities. So remember what that meant? So we're given what is the probability of a data point coming from when you know that it comes from one of the classes. So for example, the case we're talking about, it's multivariate Gaussian. We can then determine the values of the parameters, so that's kind of what we're going to be doing today, together with the class prior probabilities using maximum likelihood. Okay, so one of our favorite tools, maximum likelihood, because it's easy and often gives very intuitive answers. Okay, this requires a data set comprising observations of X along with their corresponding class labels. So that's what you're given. So requires a data set. Okay, so you're going to be given a bunch of data points that look like x1, that's a vector, and t1, x2, t2, so on. Okay, so that's your data set. So you're not given, you have to estimate the parameters, the covariance, and the means of the different clusters. Okay, so let's just look at the case of the two classes. The general case is just very easy to determine once you know the two class case. Okay, each having a Gaussian class conditional density. So again, that's important. So that's what we're going to do. And with shared covariance matrix. Okay, that's going to simplify our life dramatically. So, okay, and suppose we have a data set xn, t of n, where n equals 1 to big N. Okay, tn equals 1 denotes class C1, and tn equals 0 denotes class C2. And we're going to do that. Use that convention because it's going to make the math really simple. You can call them what you want, but this is the simplest way. And you'll see why. We denote the prior class probabilities as pi, so it's for being in the first class, and 1 minus pi for the second class. Okay, so now for data point x of n from class C1, we have the label equals 1, and hence, so the probability, this kind of joint probability of that first observation, is the probability of having come from that class times the probability of the data point itself. Okay, so what's the probability of getting a point from class 1, and then the class conditional probability of that specific data point. So this is of course going to give you that, and that's going to give you that. Okay, and similarly on the other side, the only difference is, so the thing to notice is, notice that the covariance is the same in both cases, and here it's mu1 versus mu2 in the other case, and you got 1 minus pi multiplying. Okay, so now the joint probability of all of your data is, well, you're going to assume they're sampled independently, so it's going to end up being a product of the contributions from each data point. And so now he's going to write the likelihood of these observations. Now this isn't quite right, so it's not, t is not just t1 to t of n. You actually have to include the full data set. So this should actually be, so the best way to write this is just to actually write this as probability of data given da 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 da, and data is equal to x1, t1, x2, t2, and so on. Okay, and so now if you do that way and you assume things are independent, then you can actually write your probability in this way. And notice what's happening here, right? This is a trick you'll probably remember from the when we're talking about like Bernoulli random variables. You combine them because of the way we've labeled our data. So for class 1, we've given this t of n this label of 1, and class 2 we've given, or the other class we've given it 0. What you can do is you can combine for every single data point. You can kind of write it as a combination of the two factors, the product of the two factors. So if t of n is 1, well then this thing goes through as it is, and this one just becomes 1, right? Because it's 1 minus t of 1, t of n is going to become 0, so that will just go to 1, and vice versa. So this is kind of this is the important formulation. You could kind of do it another way as well. You kind of do an if statements and kind of sort it out that way, but this is really a very simple way of doing that, right? So let me just kind of erase this a bit so to make it a bit easier to read now. So this is the formulation. So you've got your data in there. The bit we do need though, that d is equal to x I t I. So that's what should be going in there. But otherwise, yeah. And also let me just highlight these guys as well. Okay, so so it's not just these probabilities, but they're these joint probabilities raised to an exponent based on the class. It's just picking out the right class. Cool. Okay, so you're basically done at this point. So all you do is now you take the derivative of this with respect to your parameters, which are pi, mu1, mu2, and sigma, this common sigma. So we're going to do the usual thing. We're going to maximize the log of the likelihood function. Let me just highlight, just because it's important, let me just highlight this thing, and that's really important. Okay, we're going to maximize the log of the likelihood function. Okay, as the usual, exactly the usual thing. Now we just go through the steps, and it really is just very simple. So I'm not going to belabor it too much. So it just ends up, so if you write this, write this out in terms of log probabilities, you're going to get log of pi's and log of 1 minus tnth and log of 1 minus pi showing up, etc. Take the derivative with respect to pi. Pi is a scalar value. Set it to 0. And what do you get? The probability of class 1 is equal to the empirical fraction of points that came from that class. Okay, so very simple. Yeah, this is just a very intuitive result that you probably would have guessed yourself. So the maximum likelihood estimate for pi is simply the fraction of points in that class. And it's easily generalized. I'll leave that to you. Okay, now consider the maximization with respect to the means. And again, we just pick out, it's always the same. Pick out the log likelihood function, those terms that depend on mu1. So which are those terms? Well, they're the ones that show up inside that exponent. The logarithm kind of brings them out of the exponent. And now what are you getting? You're getting the sum multiplying by the label for this from mu1, right? So we've got this t of n showing up, and it's going to be 0 for the points that don't belong to that class. And there it is. Again, set the derivative to 0. Very simple. You get this relationship. It just says take the average of the points in that particular class. So let's just highlight that. Similar argument gives you the same thing, which is the mean of all the assigned to class C2. Okay, so that's all there is to it. Okay, so the only bit that's even kind of slightly tricky is the bit with the covariance. Okay, so first, so we'll just talk about this a little bit. So picking out the terms in the log likelihood function depend on sigma, we have this, right? This is coming from that, you know, that term that's hanging out at the outside. This is the 1 over the determinant to the power of to the square root. Okay, so you take the log of we're taking log, so we get the log determinant, and the square root is now hanging out outside as a 1/2. Okay, and the sigmas are hanging out in here. So now there's just a couple of things you have to do to make your life easier. Yeah, you could write it this way. So if you have to just add them all up, this is what you get. First, let's just deal with this part. So it's easy to see where that comes from because it's just this contribution, right? And that's just going to be counting. There's just going to be, for all the points that are coming from class 1, we're gonna have, this is going to be 1, so it's going to be ln sigma. And then when you're in this other class, these guys are going to be 1. So you're going to get as many data points, as many values as you have data points, divided by 2. That's coming from the square root. Ln sigma. So it's going to be easier for us. So we are just going to write this actually, we're going to work with the precision. So instead of, we'll just write this as ln of sigma to the -1. Okay? So this minus is now gone, so we've replaced that. Now where does this come from? This might be just slightly confusing. So all you have to do is remember this, the trace trick, right? So we can just write this. So this is going to be is the trace of sigma -1 xn minus mu1 times xn minus mu1 transpose. Okay, so that's just for one of them, and then if you just bring everything out, and you end up getting, so this is going to equal to, then when you sum all of that, it's going to equal to minus 1/2. Forget that bit for now. So it's going to become sum of the sum of Tn times sigma. Let's actually put that over here. Sigma -1 times sum of Tn, this is a sum, not a sigma, xn minus mu1, Actually, let me just write it more nicely down here. Okay, so we've got this n equals 1 to n of t of n of trace of sigma -1 x of n minus mu1 times x of n minus mu1 transpose. Right, so we can just bring everything inside the trace. So it's going to be the trace of the sum of n equals 1 to n and actually let's just put this outside. So sigma -1, then sum n equals 1 to n of t of n, x of n minus mu1, x of n minus mu1 transpose. Okay, okie dokie. Okay, so now what is this thing? Well, so what is this thing? Well, what the Tn is doing is just picking out the data points that belong to the first class, and so we can write this as actually n1 times the covariance of the points in that class, right? So this is n1 times 1 over n1 times sum n equals 1 to t of n. Sorry, it goes to too big of an eraser. Okay, so there we go. So sum on t of n, all that stuff. And so and this thing is just S1. Okay, so that's just the covariance. So what we get from this contribution is going to be the trace of sigma -1 of time n, and we can actually bring the n1 outside. n1 trace sigma -1 S1. Okay, so that's effectively what you do, and then the other side also gives. So then the other bit adds up, and you'll get an n2 trace sigma -1 S2, and then this n ends up dividing this, so you end up getting an expression like that. So that's effectively where you get this expression from. So just very simple. So now let's just do the final bit. So hopefully you now understand where the various bits come from. So now we've got n over 2 trace of sigma minus 1 of s. And the reason why we worked in with the sigma minus 1, why I switched over here, is because now even when we have basically, we can take derivative with respect, we can essentially parameterize in terms of precision instead of covariance. And if we do that, so if we take the derivative now, so d sigma minus 1, so it will turn out that the derivative, the log of determinant of a at least a positive, of a covariance is its inverse, and of a precision, it's the covariance. So there's going to be sigma, and then the derivative of this thing, well, this is really simple because it's just it's just going to be s. So that's all that is, and so this implies that n equals that sigma equals s. Okay, and s is this very intuitive object, which is this is the weighted sum of the covariances from the two classes. Okay, so that's all there is to it. So there wasn't much. It's just you got to do this trace trick on these guys to bring the trace in, and then it just helps to switch your variable to the precision if you want to. And that's about it. So let's see what he says in the end. So using the standard results for maximum likelihood, we get sigma equals s, which we just did, which represents a weighted average of the covariance matrices associated with each of the two classes separately. Okay, so that's all. That's all it is. And the result is easily extended to k-class problem to obtain the corresponding maximum likelihood solution for parameters. Again, it's Gaussian. It's going to be the weighted average. The approach of fitting Gaussian distributions to the classes is not robust to outliers because the maximum likelihood estimation of a Gaussian is not robust. So this is basically the same issue that we had, that if you have a point way out in the distance, it's going to tilt everything towards it. So just keep that in mind. And we've already talked about this in the past. Great. So I think that's all there is to it. Again, not much going on here. Just the main idea is formulating your problem in this way, and then just turning the crank with a couple of small tricks along the way. So hopefully that was easy and useful. And next time we will pick up and we'll just wrap up this particular section by talking about we've been looking with continuous features. So what happens if we have discrete features? So what are the decision boundaries then? Can we get linear decision boundaries then? And then also generalizing to the exponential family. So yeah, as always, please leave your comments below whether you liked it, you hated it, whatever it was. And I hope to see you next time. Bye.